All right, should I get started? Yeah, sure. All right. Okay, well, morning, everybody. Thank you for being here. I'm honored to introduce Yu-Hsuan Teng. Did I say that okay?
Yeah.
Eltha, as most of us call her. So it's been my pleasure to work with Eltha now since 2019. And I was just reflecting back on we started working together in October of 2019. Really had, 6 months before it was remote for quite some time. And then, we came back, of course, later on after that, but it was very impressive that Eltha did a lot of really excellent work with that beginning to her PhD. So really great. So Eltha got her bachelor's degree in electrical engineering and then a master's of science and physics from the National Taiwan University. She's been here since 2019 and is now going to defend her thesis on molecular gas and star formation in nearby galaxy centers. So we're going to have first 45 minutes or so. It'd be best to hold your questions unless they are extremely pressing, and then we'll have a public Q&A. Then everyone will leave except for the committee, and we'll have a private Q&A for the committee. So go ahead.
So thanks for the introduction, Karin. My name is Eltha Teng, and today I'll be presenting my dissertation on molecular gas and star formation in nearby galaxy centers. So this is, of course, a joint work with my advisor, Karin, and also with many of my collaborators in the FANGS team. So before jumping into my research on molecular gas and star formation, I want to start with a bigger picture of how gas and stars interact and evolve in a galaxy. So we know that stars are formed from the interstellar gas, but interstellar gas can actually appear in multiple different phases within a galaxy. So for example, a large fraction of the interstellar gas is actually in the warm or hot phase with temperatures up to thousands of kelvins. And so in order to form stars, these gas has to first cool down and they will form into the cold and diffuse atomic gas. And then these gas can further condense into molecules to form the molecular clouds. And next, these molecular clouds can further condense and collapse into stars. So to be more precise, star formation actually happens in the molecular gas, which is just part of the interstellar gas. But star formation is not the end, because we know that these warm stars can also produce stellar feedback process like radiation or winds that can inject energy into the ISN. And this will further disperse the molecular clouds and eventually bring all the gas back into the warm, either neutral or ionized phase. So this cycle can continue to go on and on. And so to understand how galaxies evolve, we have to understand each of these individual processes. And this can be done by connecting multi-wavelength observation of galaxies. So here, what you're looking at is the same galaxy, but observed at different wavelengths using different telescopes. And so each of these panel here basically is tracing emission from different phases of the ISM or of the stars. And for my dissertation, I will be focusing mostly on this process from molecular cloud formation to star formation. And so in the presentation, you may be seeing a few images like this, which shows the molecular gas observations in different galaxies. So one of the data set, for example, I will be using the FANGS ELMA survey. So FANGS ELMA survey is currently the largest high-resolution molecular gas survey across nearby galaxies. So here you are seeing almost about 100 nearby galaxies, and you can see detailed variation of molecular gas within them. And these galaxies covers a wide range of morphological environment as well. So going into my research, I've been studying star formation and molecular gas in massive spiral galaxies, including our Milky Way and nearby galaxies. So the overarching goal is to understand how star formation that happens at small scales are connected to the large scale environment that is driving galaxy evolution. So to do this, my research probes into different phases of molecular gas. including the cold and dense molecular gas, which we know is important because these dense gas reaching densities like 10 to the fifth or 10 to the sixth per cubic centimeter are very closely associated with the small scale star formation process. And also a big part of my dissertation focused on the bulk molecular gas. So this can tell us the overall distribution of molecular gas within a galaxy that is fueling star formation sites in the galaxy. And this is typically traced by the rotational transitions of carbon monoxide, which you will be hearing a lot more details later. And more recently, I've also started to expand my research into the warm and hot molecular gas, because as I mentioned earlier, these warm gas can be reflecting the energetic stellar feedback process that we know is quenching the star formation activities in galaxies, and they can have huge impacts on the efficiency of star formation. So by connecting these different phases of molecular gas at different evolutionary stage, I'm hoping to obtain a more complete picture of the interplay between molecular clouds, star formation, and stellar feedback within galaxies. So a quick overview of my dissertation. So it is focused on the bulk molecular gas traced by CO. But one big problem for current molecular gas measurements using CO is that they rely heavily on the knowledge of the CO to H2 conversion factor, alpha CO, or some studies use XCO. So to address this long-standing issue of alpha CO, my dissertation includes 3 papers where we started from measuring molecular gas properties and alpha CO across several nearby barred galaxy centers. And then based on these measurements, we have identified the physical drivers and the key observables that can be used to trace these alpha CO variations. So this further led us to develop a new general alpha CO prescription for star-forming galaxies. And finally, we also investigate how these alpha CO variation would impact our knowledge on star formation efficiency in nearby galaxies. So our motivation is to study star formation in galaxies. And we know that stars are formed in the molecular gas phase. So this means that the star formation process is controlled by both the amount of molecular gas and the efficiency of the gas being converted into stars. And these properties can be studied through the well-known molecular Kanin-Schmidt relation, which you can see from these figures, that star formation rates are found to be tightly correlated with the molecular gas surface density across a wide dynamic range. And so this relation has laid an important foundation for many extragalactic star formation studies, because you can imagine that these roughly constant slopes here are basically suggesting that star formation efficiency seems to be constant throughout different regions or different galaxies. However, to either study the molecular gas amount or star formation efficiency, we have to accurately trace the molecular gas. But unfortunately, the main component of the molecular gas, which is the molecular hydrogen, it is not directly observable in the cold molecular gas where star formation happens. So this is because even the lowest energy transition of H2 requires about a gas temperature of like 100 Kelvin to be excited. And so the most common way to trace molecular gas is to observe the second most abundant molecule, the CO emission, and then people apply a CO to H2 conversion factor so that they can obtain the total molecular gas mass from the CO line flux. So you can think of this alpha CO as an empirical mass to light ratio. And previous studies have found this alpha CO to be roughly at a constant of about 4.4 across the Milky Way disk molecular clouds. And so many studies simply assume this constant Milky Way value to derive molecular gas mass and other properties in all kinds of regions or galaxies. But alpha CO should not be a constant, because even in theory, we know that alpha CO should vary with molecular gas properties. For example, it's clear that alpha CO should vary with terms like metallicity or CO to H2 abundance, because these basically determines the true amount of CO or H2 we are observing. And also, alpha CO should clearly depends on like density, temperatures, and velocity dispersion, because these terms determine the emissivity properties of CO, which means how much CO will be emitted per a fixed amount of molecular gas. And these emissivity relevant terms are actually really important because we know that the low J CO lines we are observing are usually optically thick. So this means that for the CO spectrum we are observing, the peak intensity is set by the temperature at the molecular cloud surface instead of reflecting the true amount of CO along the observed line of sight. And so you could imagine that if the peak is set and if the velocity dispersion increases, there will be more CO emission escape from the cloud and lead to higher CO intensity per unit gas mass, and that would decrease alpha CO. And so all these are just showing that alpha CO is not a simple constant value, but it is tied to the molecular gas conditions like temperatures and velocity dispersions. So now we know that alpha CO depends on molecular gas properties. So we would expect that regions with different environments should have different alpha CO values. And this is exactly what recent studies have found. So in this figure here, you can see a bunch of alpha CO measurements or alpha CO predictions from simulations. And you can see that alpha CO can vary up to orders of magnitudes in different environments. So for example, you can see that for low metallicity galaxies, they typically have much larger alpha CO than the typical Milky Way disk value people are assuming. And this is probably because in these low metallicity environment, there is less dust to protect CO from being photodissociated. And also for very active galaxies like LIRS or ULIRS, you can see that they typically have lower alpha CO than the Milky Way value. And this is because the gas in these ULIRS may have higher temperature or turbulence that can increase the CO emission and decrease alpha CO. And another interesting regime is the galaxy centers. So although earlier I mentioned that people have found a roughly constant alpha CO across the Milky Way disk, but even in the center of our own Milky Way, we're found to have 3 to 10 times lower alpha CO than the typical Milky Way value. And interestingly, recent studies have also found that alpha CO is systematically lower towards the central kiloparsec in many normal star-forming galaxies. So it is possible that activities in galaxy centers like nuclear starbursts or gas inflows, these kind of dynamic effects can also alter the alpha CO values in this region. So this shows that emissivity dependent terms are really important. And this actually also makes galaxy centers great targets to study the relation between alpha CO and molecular gas properties, because galaxy centers can be relatively nearby to us, but they can also span a wide range of environment that connects normal disk conditions to like extreme conditions, as we see in ULIRS. So now we see that alpha CO does vary within and between galaxies, but why is studying alpha CO variation important? So I've shown that alpha CO is the basis of measuring molecular gas mass, and it is tied to the molecular gas conditions. But it is also important to realize that alpha CO not only affects the molecular gas mass, but also every star formation properties that are inferred from the molecular gas mass. And this includes a lot. So this includes even the Koenig-Schmidt relation I showed in the beginning. And here I'm also listing a few critical parameters that have been widely used in star formation studies. And you can see that all these parameters depends on the molecular gas mass. So this means that alpha CO can have great impact on the estimation of these star formation properties. So just as an example here, This is recent studies that aims to distinguish whether starburst galaxy centers, like these data points, so whether their high star formation rates are more driven by higher molecular gas mass fraction or higher star formation efficiency. And so it looks like most of the data points align pretty well on this one-to-one relation. So this would suggest that molecular gas mass and star formation efficiency probably contribute equally to the starburst. But the problem is these data points were assumed to have a Milky Way constant alpha CO. And so you can see that you can see from this arrow that even with just a factor of 2 decrease in alpha CO value can bring all these data points to this very lower right portion of the plot. And this will give a completely different conclusion that star formation efficiency is totally dominating over the molecular gas effect. And another example here studies the star formation efficiency per free fall time across a single galaxy. And the idea is similar. It seems like most of the data points aligns well with this red line, which suggests constant star formation efficiency per free fall time. But we know that galaxy centers, especially, probably they don't have a Milky Way constant value. So you can see if it actually has lower alpha CO value, it will be moved further away from this red line, and this will no longer suggest a constant efficiency per free fall time. So these examples shows that using a wrong alpha CO can really bias the estimation of many important quantities. And actually nowadays, alpha CO has become the dominant source of uncertainty in current molecular gas measurements. And so to break through this limitation caused by large alpha CO uncertainties, we have to measure alpha CO across sufficient galaxy sample that covers enough environment conditions so that we can understand how alpha CO behaves and establish a good prescription to predict alpha CO, so that eventually we can come back and revisit all these quantities and see how they would revise our knowledge on galactic star formation. So there are a few ways to measure alpha CO, and their basic idea is actually similar, that we can estimate the total molecular gas mass using different methods, and then we compare with the observed CO emission. So for example, we can estimate the total molecular gas mass using optically thin tracers like CO isotope logs, dust, or even the gamma ray emission. Or we can also rely on some assumptions. For example, we can assume that all molecular clouds are under virial balance so that we could use the measured cloud size and line width to derive the virial mass. Or some people may assume that star formation efficiency is constant as suggested by the Kennebec-Schmidt relation, so that we could infer the cloud mass from the measured star formation rates. But all these methods have their limitations. And it turns out that for extragalactic sources, the most realistic way to measure alpha CO is to use CO isotope logs and dust. And so in this presentation, you will be seeing we are using both alpha CO measurements from CO isotope logs and dust. And so in our work, we always compare these two methods to ensure consistency or calibration. And a little more introduction on CO isotope logs. So CO isotope logs means CO, but with different composition of the isotopic C or isotopic O. So for example, the CO we have been referring to so far actually means the most typical 12C 16O. So this 12CO line is usually very bright and optically thick in molecular cloud observations. But there are also rare CO isotope logs like the 13CO or the C18O. So for example, for 13CO, the abundance is usually 1 or 2 orders of magnitudes lower than the typical 12CO. And C18O is even less abundant than 13CO. So you could imagine that 13CO and C18O are mostly optically thin in molecular clouds, which means they can be very useful in tracing the molecular gas. But because of their low abundance, you could imagine that these isotopic log lines are also very faint in emission. So it is actually only recently that we can use the state-of-the-art millimeter telescope ELMA to observe these 13CO and C18O lines across nearby galaxies. And so here I'm listing a few CO isotopic log lines with their frequency, and you can see they're all covered by different bands in ELMA. So as a first step to understand alpha CO variations, we target 3 nearby barred galaxies because these galaxies were suspected by previous lower resolution studies that they have substantially lower alpha CO value. And so we use ELMA to observe multiple 12CO, 13CO, and C18O lines towards the central 2 kiloparsec region of these galaxies. So you can see that the regions we observe are like focusing on the central bright and compact region that is even within the stellar bar of the galaxy. And I want to emphasize again that not only we include 12CO lines, but also many other 13CO and C18O lines that are optically thin. And we observe up to the 3-to-2 transitions. So this means this combination of lines really give us good constraints on the excitation conditions and optical depth variation across our galaxies. Also, for all 6 lines we observe, they all reach an angular resolution of at least 100 parsec scale, which means that we are probing at the giant molecular cloud scales in these galaxies. So this is our result for the first galaxies. You can see our observed maps. All 6 lines are very well detected across the center of galaxies. And on the right, you can also see various line ratio variations among different substructures. So one notable thing about this galaxy is that there is a clear star-forming ring at the center around the compact nucleus. And this ring is also connected to 2 inflow arms, which is driven by the stellar bar at the galaxy center. And interestingly, we found that these gas inflow arms also has significantly higher CO to 13CO line ratio, and actually also the CO to C18O ratio, which probably suggests a very low optical depth that can have huge impacts on alpha CO, but I'll talk more about this later. But these are our other observed galaxy. It is NGC 3627. So this galaxy is more inclined and it has an AGN in its galaxy center. So you can see a bright and compact nucleus well detected in all 6 lines. And on the line ratios, you can also see that the nucleus really stands out from other regions. And the last galaxy we observe is NGC 4321. So this one is more face on. And again, you can see distinct line ratio variations that separate different substructures in the galaxies, like the nucleus, the inner and the outer arms all have different line ratio. So this clear line ratio variation across all 3 galaxy centers are suggesting that the molecular gas physical conditions also varies a lot across these regions. So to more precisely determine the physical conditions of these of different regions in these galaxies, we use radiative transfer model with Bayesian likelihood analysis to model all 6 lines we observe, and we fit with the observations to constrain best fit solutions and the likelihood distribution for each parameter of interest. So I won't go into the technical details for the modeling, but the main idea is that we simultaneously constrain all 6 parameters that are relevant to controlling alpha CO variations, including the CO opacity, temperature, density, and the isotope log abundances. And then we do this kind of modeling pixel by pixel so that eventually we can obtain maps like this, which shows our model solution for each parameter and each pixel. So from these maps, we can already see some gas property variations across the centers. For example, we can see that temperatures are typically higher towards the nucleus, and the density also enhanced in the very center of galaxies. And there are also some abundance variation as well. So these are already very interesting results. But our further goal is to compare these molecular gas properties with the alpha CO distribution, which we can also derive in a similar way using the same model parameters, the CO intensities and CO to H2 abundance ratio. So here are our derived alpha CO maps. But more clearly, I want to show this plot, which is a cross comparison of three gases. You can see how their alpha CO vary with the galactocentric radius. So first of all, you can see that all the pixels in our observed region has way much lower alpha CO than the typical Milky Way disk value. So you can see typically we get 5 to 15 times lower alpha CO value across these galaxy centers. But also you can see large variations in alpha CO in even just one single galaxy center. And the most extreme case is actually the inflow arms of NGC 3351, which corresponds to this structure here. So later, I will show that this is actually a very extreme case where we find CO is optically thin. So that means all the CO emission is escaping from the cloud, and that would increase the CO emission and decrease alpha CO. So in this region, we find alpha CO can even reach 20 to 30 times lower than the typical Milky Way disk value. So now comes the interesting part, because we have derived molecular gas properties and alpha CO, then we can further explore their correlations and see what is exactly driving these alpha CO variations. So first of all, we found a very strong correlation between alpha CO and CO optical depth in this optically thick region. So the optically thin region basically covers all the pixels of these galaxy centers, except for the NGC 3351 inflow that I've been mentioning a lot. So we find that this strong correlation actually explains about 80% of the alpha CO variation we observe across all galaxy centers. But also you can see that to the second order, alpha CO also decreases with the gas kinetic temperature. And this also makes sense because higher temperature would also increase the CO emission and decrease alpha CO. But one thing that is clear from these plots is that the scatter in the temperature relation is much larger than the scatter in the optical depth relation. So it's clear that these optical depth effects are more dominant in driving alpha CO variation in these regions. So now, knowing that the CO optical depth is the main physical driver of alpha CO, our next step was to think if there's a chance we can identify observational tracers for optical depth, which is the main physical driver, so that we can use some tracers to predict alpha CO from observations. So if you recall, I have been emphasizing the inflow regions of NGC 3351 because it is the region where we find extremely low alpha CO, and it is also the only region with optically thin molecular gas. So we think this suggests that the low alpha CO is probably because of the increased CO emission due to the very low optical depth. And we found that this scenario perfectly explains why we are observing significantly higher CO to 13 CO ratio and increased CO line width along these inflow arms. Because you could imagine that larger line width would reduce the CO optical depth and further lead to increased CO emission that leads to the higher line ratio and the decreased alpha CO. So it seems like the CO to 13 CO line ratio and line width is telling something about alpha CO, but this is just result on one galaxy. Now, an even more exciting result is that after combining all three galaxy centers, we do see a clear trend of alpha CO decreasing with both the CO to 13 CO ratio and the CO line width. So this means that both observables can be good observational tracers for alpha CO variations. But so now the critical next question would be whether these relations can also hold across a large sample of galaxies. So you can see that currently we only have complete isotopologue data set for 3 galaxy centers. And this is because, as I mentioned earlier, CO isotopologues are faint. So actually, these observations on even just one single galaxy takes a lot of time and is expensive. The modeling also takes a lot of effort. So we had to figure out a more efficient way to test these relations systematically across galaxies. And we figured that we can use dust observations because dust observations can be more easily to obtain across large samples of galaxies, although the trade-off is that they typically have much lower resolution at kiloparsec scales. But still, it should still be possible to test the relation which we identified using high-resolution CO isotopologues on the dust measurements and see whether the relation holds. And it turned out that the alpha CO dependence on the line width is working surprisingly well across different galaxies. So here you can see the data in blue is showing recent dust-based alpha CO measurements at 2 kiloparsec resolution. And it is correlated with the 150 parsec scale velocity dispersion measured from the FANGS data sets. And so this whole data covers 12 barred and non-barred galaxies out to a galactocentric radius of 10 kiloparsec. So you can see the trend of this data aligns very well with the orange dashed line here, which is exactly what we saw on the 3 barred galaxy centers. So it was really exciting for me to see that this same relation not only holds for barred galaxy centers, but also for non-barred galaxies and even out to the galaxy disks. So based on these measurements, we have constructed a new alpha CO prescription as a function of cloud scale velocity dispersion. So you can see that the scatter with respect to the prescription is actually pretty small. It is only about 0.1 dex. And this is actually the smallest scatter among existing alpha CO prescription. And we think the reason is because the cloud scale velocity dispersion here is directly tracing the physics that alters alpha CO, which we identified is the optical depth variations. And also another advantage of our prescription is that it requires only the CO observations, which we already need for tracing molecular gas. So it doesn't require any ancillary multiband data to be able to predict alpha CO. And another interesting thing we also found is that the velocity dispersion here may also be reflecting other correlated properties. So for example, we know that metallicity can also be important drivers for alpha CO. So we also explore how the measured alpha CO varies with metallicity. So here you can see alpha CO does decrease with metallicity, and the trend is actually pretty consistent with recent metallicity-based alpha CO prescription. But first of all, we can see that the scatter is much larger than the velocity dispersion trend. But more importantly, we want to know whether this variation with metallicity can explain the residual we are observing in our velocity dispersion prescription. So in the bottom panel, we correlate the residual from our fit with metallicity here. And on the right, we did something similar that we correlate the residual from metallicity fit with velocity dispersion. So surprisingly, we found that there is almost no correlation between the residual from our prescription with metallicity. But on the right, there is the residual from the metallicity fit clearly decreases with velocity dispersion. So this means that somehow the metallicity variation is already included in our velocity dispersion trend. And we have actually checked that this is because velocity dispersion and metallicity are correlated because both of them varies with the galactocentric radius. And finally, we want to investigate how the alpha CO variation would impact our knowledge on star formation efficiency. So we apply our prescription to 65 galaxies from the FANGS data set. And we want to see how the derived Koenig-Schmidt relation would differ from using a Milky Way alpha CO. So from the figure below, it's clear that using our prescription clearly reveals a steeper Kankar-Schmidt relation towards galaxy centers, and this will suggest higher star formation efficiency. But comparing to the right, you can see that using a Milky Way alpha CO simply leads to a smooth and constant star formation efficiency in both the centers and the disks. Also, if we compare directly the absolute value of molecular gas mass, you will see that using a Milky Way alpha CO can overestimate the total molecular gas mass by a factor of 5 in galaxy centers. So this shows us that the choice of alpha CO can really affect our understanding on the fundamental star formation law. And even more interestingly, we further separate barred and non-barred galaxies, and we compare the derived gas depletion time using different alpha CO prescriptions, including the most commonly used Milky Way alpha CO and the metallicity-based alpha CO. Also, we want to compare our new prescription with the Bellato prescription, which try to account for CO emissivity variations. So first of all, we saw that across the galaxy disk regions, all 4 prescriptions lead to similar depletion time distribution. And it's regardless of whether it is a barred or non-barred galaxy. But interestingly, when we go into galaxy centers, now we clearly see that using a Milky Way alpha CO or a metallicity-based alpha CO gives us longer depletion time that can be 3 to 5 times longer than using our prescription or the Bellato prescription. And even though the Bellato prescription seems to predict a generally shorter depletion time that is similar to our average value, but we found that only our prescription reveals a clear separation between barred and non-barred systems. So you can see a clear shift toward shorter depletion time for barred galaxies. So this would suggest that the star formation efficiency is increased in barred galaxy centers. And if this is true, this will affect our current understanding of molecular gas concentration in nearby galaxies, in galaxy centers. Because you can imagine that previous studies using Milky Way constant alpha CO are mostly overestimating the molecular gas mass in these galaxy centers. So people tend to think that the high star formation rates in barred galaxy centers is due to the larger amount of molecular gas in those regions. And this seems to make sense if star formation efficiency is roughly a constant. But what we found with our new prescription is that there is actually a similar amount of molecular gas between barred and non-barred galaxy centers. And it is probably because of the increased star formation efficiency in these regions that makes star formation rates higher, instead of there is really more amount of molecular gas. So this brings up a very interesting question, that what specific conditions is driving the higher star formation efficiency in these regions? And to answer this question would require more future work, because the interesting thing here is that the conditions that could be driving star formation efficiency variations, such as the gas structure, density, or dynamic effects. So these conditions are the same condition that would alter the CO opacity and alpha CO variations. So only when we have the correct alpha CO, then we can move on to reveal the true variation of star formation efficiencies. So one of our future direction is to study the warm molecular gas that can be reflecting the energetic feedback process, which we know are important in varying the star formation efficiency. And this can be done by, for example, using the recently launched JWST. Their mid-infrared spectrum covers the whole H2 ladder. So just like this recent study, it is showing 7 well-detected H2 rotational lines in the center of M83. And another way to study molecular gas, the warm molecular gas, is using the high J CO transitions. So currently, we already have data from Herschel that includes high J CO lines up to CO 9 to 8 in like 20 nearby galaxy centers. So these kind of studies can allow us to systematically study the impact of stellar feedback on star formation efficiency. And another direction I'm very excited about is to extend our current prescription to cover even more extreme environments, like covering like Eulers down to low metallicity dwarf galaxies, or even in the molecular outflow regions. So recently, we have already expanded my multi-line modeling code onto more extreme systems like the starburst merger antennae. So what we found is that there is a singularly tight correlation between alpha CO and optical death. And this also leads to similar trends with the observed line ratio and velocity dispersion. But one thing we haven't been able to explore is to systematically test the alpha CO dependence on the line ratio across large sample of galaxies. And this is especially important because this will allow us to test whether CO opacity is the only key driver everywhere over the galaxy disks and the galaxy centers. And we haven't been able to do this because there is currently no sufficient high resolution and sensitive 13CO line mapping across nearby galaxies. So you can see that current survey, even at kiloparsec scales, are still very limited by the signal to noise ratios. You can see the measurements are still sparse and the scatter is pretty large. So I have been working on several new ELMA proposals to target cloud scale observations of the 13CO line across the nearby galaxies where we have alpha CO measurements. And also we have another program that we propose to target multi-line CO isotope log observations in a more quiescent set of galaxy centers. And also we have been working a lot with theorists to compare our alpha CO measurements with numerical simulations. So this is some result I didn't show earlier, but basically we have found that current ISM simulations seems to always overestimate alpha CO comparing to our measurements on galaxy centers. And we think this is because the current simulation that give alpha CO prediction, they typically don't include effects like the gas inflows or the large scale turbulence that we found is important in galaxy centers and starbursts. And so interesting direction is to test whether adding these effects into simulation can give us a better prediction of alpha CO that would match the observations. And finally, as I mentioned earlier, alpha CO not only affects star formation efficiency, but also many other important quantities like cloud evolution in timescales or the cloud dynamic pressure, virial parameters. So a systematic study on all these impacts should be important, and it might also revise our current knowledge. And more importantly, these physical properties can be even more easily to compare with the simulation results. So to conclude, some key findings from my dissertation includes that we reveal lower alpha CO in galaxy centers, but with large variations on molecular cloud scales. And because of these high quality alpha CO measurements, we further disentangle the physical drivers of alpha CO and identify that CO opacity is the main physical driver. So this led us to propose 2 new observational tracers for alpha CO, which laid the foundation for benchmarking alpha CO calibration in galaxies. And we have also tested our new prescription led to enhanced star formation efficiency in our galaxy centers, which also gave new insights on the fundamental star formation law. So all these results have opened up many exciting questions and new direction for future star formation research. So finally, I want to thank many people that helped me along the way. So first of all, of course, I'm really grateful to my advisor, Karin, who I think I'm really lucky to have her as my advisor. She is like the greatest advisor I ever hoped for. Yeah, I think she always motivates me and always makes herself available whenever I needed help. And I actually still remember that back in my first year, I was actually quite frustrated with all the physics courses and doing lab TA, but it was really because working with Karin and doing research had so much fun. So like I decided that I have to hang in there. Yeah. And yeah, I also want to thank Allison, Raphael, James, and Shelley for being my thesis committee members. And especially I want to thank Allison for also supporting me during my second year, working on another very interesting research project. And next comes my colleagues in Team Nearby Galaxies and also many collaborators in the FANGS team. So I think a special mention to Ida, who has really helped me a lot during my first 2 years here, whether it's on research or on settling down or even daily life during the pandemic time. And I'm also especially thankful to Alberto, Adam, and Jai, who have always been giving me useful advice and critical comments on my research and on my job search. Also, I want to acknowledge NRAO, NSF, and Taiwan Ministry of Education for funding my PhD research, and also for both the physics and ANA departments for all the administrative support. And finally, I want to thank my family and friends who have always been there supporting me and believe in me. And especially, I want to thank my partner, Herman, for always being there and encouraging me and being my best friend. So I think I'm very lucky, especially that we can fly all the way here and do a PhD together. It's just still feels like a dream for me. So finally, thank you to everyone who has helped along the way, and thank you all for listening.
All right, so I think now we have some public Q&A, and folks who are on the Zoom, you can maybe raise your hand, but start off with any questions in the room.
So thank you. I learned a lot. Incredibly impressive body of work that you've done since you've been here. My question was about when you were talking about doing the multi-line fitting, and then you mentioned that you're doing it pixel by pixel. How do you account for potential correlations between neighboring pixels, or do you assume that there isn't any? Like, it seemed like each pixel kind of had its own fit, but presumably regions that are next to each other should have some sort of correlation.
Yeah, that's a really good question. So for the maps I've been showing, it is actually all under Nyquist sampling. So which means it is the, like, we didn't oversample our maps. So this is because we want to minimize the correlation between each pixel. But of course, there are also probably some correlations with nearby pixels. And in our modeling, we did try to account for correlations for observation in the same band. Yeah, so observing with the same Elma band. But yeah, so that's.
Other questions? Anyone online?
Awesome job, Eltha. This is great. I have a question, and I wonder how much you know about it. You mentioned comparing your methods. I think it was you had a lot of histograms of barred and non-barred comparing it to Bellato's method. What's the difference between your work and his?
Yeah, let me bring up the slide. You are mentioning the histograms, right?
Yeah.
Okay.
Yeah.
So what I was talking about, like the comparison between ours and Bellata prescription. So the similarity is that we both suggest lower, shorter depletion time. But the main difference with the Bellata prescription is that you can see this is the median for barred and non-barred, and there is no significant separation on the Bellata prescription, but our prescription reveals like more than a factor of 3 separation in barred and non-barred. So the Bellata prescription basically suggests that all galaxy centers have this shorter diffusion time. But our prescription suggests that it is the large galaxy centers that is having high star formation efficiency rather than all galaxy centers.
And I guess what's the difference in like your methods? Or like how you get the different from
Oh, yeah. So yeah, I should have explained this more on the Blotto prescription. So Blotto prescription is actually as a function of metallicity and stellar mass surface density. So it's a totally different prescription from ours. Yeah.
cool, thanks.
Ryan?
That was a great talk. I just have a small question. For the results with metallicity, I was just curious, was this measured with a single strong line calibration for the metallicity? And if you experimented with other calibrations just to see how the results might change?
Yeah, so. Yeah, so this is, I think the metallicity measurement is calibrated using, not using strong line, but with the, it's ETA, in ETA's measurements. Yeah, so because these alpha CO values are from the dust measurements, and for those samples, they are using not the PPO4, but the other one, the PG16S calibration. So yeah, so these are based on PG16S calibration. But we also really want to use like strong line measurement, but of course, because we are testing on large galaxy samples, and that is, we don't have that much strong line measurements across large galaxy samples, so we have to use other methods.
Any other questions from the audience? Anyone online wants to ask a question? Okay, then I think let's thank Eltha again.